So, class, what I'm going to discuss today is known as your meter bridge. So what is a meter bridge? Very simple. The word itself, the name itself gives us the definition. Meter bridge, a bridge which is 1 meter long. Is it okay? That is known as meter bridge. This meter bridge, we also call it as slide wire bridge. S-L-I-D-E. Slide wire bridge. Meter bridge, or also we call it as slide wire bridge. Okay. Why is it called a meter bridge? Why is it called a meter bridge? Because the wire that I am going to use in this bridge is 1 meter long, or we can say 100 centimeter long. 1 meter makes 100 centimeter. Okay. We call this as meter bridge because the wire that we are going to use here is 1 meter long, or we can say 100 centimeter. And that wire is tightly stretched between the 2 points A and B. A and B. All right? The wire that I'm going to use here is 1 meter long, and that wire should be tightly stretched in between the points A and B. In between the points A and B. Okay. So this is the wire. This apparatus is also, or this arrangement is also called as meter bridge because the wire that we are going to use here is 1 meter, and that wire is tightly stretched in between the points A and B of 2 copper strips. This is a copper strip. This is also another inverted L copper strip. L inverse, we can say. All right. Okay. So the wire of 1 meter long is tightly stretched in between the 2 points A and B of 2 copper strips. You can take copper strips or you can take silver strips. All right. So these are your copper strips. Okay. Inverted L copper strips, you can say that. Now, the type of wire that we are going to use here should be an alloy. Should be an alloy, maybe say manganese or tungsten. When I discussed about color-coded carbon resistors, that topic, if you can remember, that particular class, if you can remember, we discussed things about the alloy resistances. Is it okay? So this wire that we are going to use here is an alloy resistance. Maybe tungsten or a manganese. Why wire of alloy resistances are used? Why do we use alloy resistance wire here? Because alloy resistances are temperature independent. Is it okay? If this wire is not a temperature resistant, then what happens during the experiment? While performing the experiment, the temperature will increase, and as the temperature increases, the resistance of the material will be disturbed, and so you do not get any value, any specific value. Is it okay? So the type of resistance that we are going to use here is an alloy resistance, maybe a tungsten, or a manganese, because alloy resistance are temperature independent. Let me make a note of it. The wire that we are going to use here is alloy resistance. Is it okay? Alloy resistance, say manganese, or tungsten. Because these alloy resistances are temperature independent. Okay, these alloy resistances are temperature independent. So the wire that I'm going to use here is an alloy resistance, which is temperature independent. And so with the increasing temperature also, the resistance of this wire will not be affected. Is it okay? Yes. Now, what I'm going to do here is, let me explain the construction. Let us look at the construction. And a wire, okay, a wire of 1 meter, which is alloy resistance, is tightly stretched in between 2 points A and B of 2 inverted L copper strips. There is another copper strip placed in between the 2 copper strips. Okay. There is another third copper strip which is placed in between the 2 inverted L copper strips. Now, the ends of the 2 inverted copper strips are connected to the 2 terminals of the cell. Suppose this is a cell of potential difference V, a battery of potential difference V. So the 2 ends of the inverted L copper strips are connected across the 2 terminals of the cell. Is it okay? There is a scale of 1 meter or 100 centimeter, which is placed adjacent to your wire, to your 1 meter wire. There is a meter scale, a scale of 1 meter long is placed adjacent to this wire, to this alloy resistance wire. Is it all right? Now, let us now, in between these 2 copper strips, we connect a resistor. We connect a resistor of unknown resistance. In between these 2 copper strips, we connect a resistor of unknown resistance. Or you can say we connect a resistor whose resistance has to be determined. So since the resistance of this resistor is not known, so we can take it to be X. We can take it to be X. The resistance of this resistor is X. And also on the space in between these 2 plates, in between these 2 copper strips, on the space in between these 2 copper strips, we connect another resistance, say a resistance box. We connect a resistance box. Resistance box, okay, is something which you can introduce any amount of resistance, you can introduce any desirable resistance, you can introduce, okay, any amount of resistance. So this resistance box denoted by R is your known resistance or desirable resistance. You can introduce any amount of resistance through here. You can introduce a resistance of 1 ohm, you can introduce a resistance of 2 ohm, you can introduce a resistance of 3 ohms. Is it okay? But not more than that. So On the space in between these two copper strips, a known resistance has been connected. So R is your resistance box. Resistance box, which is your desirable resistance, or in very simple words, we can call it as known resistance. Known resistance. Is it okay? Now, let's take another point C, okay, or on this copper strip. We have introduced another point C on this copper strip, and from this particular point C, I'm going to connect a galvanometer denoted by G, galvanometer. Galvanometer is an instrument which can detect the presence of even a slightest current. Okay, galvanometer is an instrument which can detect the presence of a very small amount of current, even in microamperes. All right? Yes. Now, the other end of the galvanometer is connected to a jockey. The other end of the galvanometer is connected to a jockey. Jockey is a metallic rod having knife edge. Jockey, Jockey. Jockey. What is jockey? Jockey is a metallic rod having knife edge. So that is the construction. Is it okay? Now, as the circuit is complete, what you are going to do is you are going to slide this jockey over the wire AB, which is 1 meter long. Is it okay? And your aim is to find the null point. Your aim is to find out the null point of your bridge. Null point means when the bridge is balanced. That is, okay, let's say this is your D. Is it okay? Yeah. So I think you are clear with the construction of this arrangement, right? Okay, that is all about the construction of this meter bridge. Is it okay? Okay. Now, what we are doing here is, what I'm going to do is, after the circuit is complete, after the circuit is made correct, what you do is, you take the jockey, and you hold it, you press it at this point of the wire. You hold the jockey and you press it at this end of the wire. Is it okay? At one extreme end of the wire. Then the galvanometer will show full-scale deflection in the opposite direction. The galvanometer will show full-scale deflection in the opposite direction. So let me explain. If this is the galvanometer, this is your 0, this is your say 10, 20, this is your 30. This is your 10, this is your 20, this is your 30. This is your galvanometer. There is a pointer here, there is a needle on the galvanometer. So as you take the jockey and you press at this extreme end of the wire, then the galvanometer will show full-scale deflection in the opposite direction. Is it all right? The galvanometer will show full-scale deflection in the opposite direction. Now you take the jockey and then you press it at this extreme end of the wire. You take the jockey again and press it at this extreme end of the wire towards B or at B. In that case, the galvanometer will show full-scale deflection in the opposite direction. Are you getting that? At any point towards the end A of the wire, if you press the jockey, then if you hold the jockey and press it at this extreme end of the wire or at A, then the galvanometer will show full-scale deflection in the opposite direction. Again, as you take the jockey and press it at this extreme end of the wire at B or towards B, then also the galvanometer will show full-scale deflection in the opposite direction. So when you press the jockey here, galvanometer is going this side deflection. When you press it here, the galvanometer is showing this side deflection. That means there is a particular point in between A and B. There is a particular point in between A and B in which the galvanometer will not show any deflection. The galvanometer will point at 0. That is the null point. That is the null point of your meter bridge. In such a case, your meter bridge will be balanced. Is it okay? So that is what we are going to determine. Null point of the bridge, and that will be the balance point. Balance point of the bridge, where the galvanometer does not show any deflection. Is it okay? In such a case, the bridge is said to be balanced. In that case, if the bridge is balanced, in that case, no current will flow through the middle resistor. That is what we studied in Wheatstone bridge, right? If your Wheatstone bridge is balanced, then no current flows through the mid resistor, right? It will only flow through the arm resistors, not through the mid resistor. Is it okay? So that is the balance point. That is the null point that we have to find out in this meter bridge. Are you clear? Okay. Now let us do it. Now you see, you take the jockey and you press it at one extreme end of the wire, say towards A. All right. Take the jockey and press it at one extreme end of the wire, say at A or near A. Then galvanometer will show full-scale deflection in the opposite direction. Now, you slowly slide the jockey towards the point B. You slowly slide the jockey towards the point B. See, you have started sliding the jockey from A, right? So A is your starting point. A is your starting point. So your A will be at 0 centimeter. Is it okay? And since the wire is 1 meter long, the point B will be at 100 centimeter. Are you following that? Are you following that? You take the jockey and then you start sliding from the point A. So point A is your starting point, so it will be considered at 0 centimeter. And the extreme end of the wire is at B. The other end of the wire is at B. And since the wire is 100 meter long, point B will be at 100 centimeter. Is it clear? Yes. Now what you do is, it's very simple. It's very simple. Take the jockey, okay, and start sliding on the wire. You start sliding the jockey on the wire starting from point A. If you take the jockey and hold it and press it on the wire at A, the galvanometer will show full-scale deflection in the opposite direction. Now, You slowly slide the jockey towards the other end, then the deflection in the galvanometer will start to decrease. And at some point on the wire, say at D, the galvanometer will show no deflection. That is the null point of the bridge, or that is the balance point of the bridge. Let's say that that particular point is D. Is it okay? Yes. So you have started to slide the wire, the jockey from A, and you got the null point at D. So let the length AD of the wire be L. Let the length AD of the wire be L. Then what will be the remaining length? Of the wire? The entire length of the wire is 100 centimeters. So if we have taken the length AD of the wire to be L, then the remaining length of the wire BD will be 100 minus L centimeter. Is it okay? 100 minus L centimeter. So class, D is the point where the galvanometer does not show any deflection, which is the null point and hence the balance point of the meter bridge. In such a case, at this particular point, your meter bridge is balanced. Are you clear with that? Yes, maybe. Now you see, if I say, if R is the resistance, if smaller, okay, smaller is the resistance per unit length of the wire, per unit length of the wire. If smaller is the resistance per unit length of the wire, no? Then what will be the resistance across the wire AD? Can anyone comment here? If R is the resistance per unit length of the wire, in 1 unit length of the wire resistance is R. Then for the wire of length AD, what will be the resistance? For the length AD of the wire, what will be the resistance? For the length AD of the R is the resistance per unit length. So for the length AD of the wire, what will be the resistance? Yes, very good. One student commented, this student commented first. So for the part AD, for the length AD of the wire, the resistance along the length AD will be R times L. Very good. Is it okay? Will be R times L. For 2 centimeter length of the wire, the resistance will be 2 times smaller. Is it okay? So for L length of the wire, the resistance will be R times L, right? Now the remaining part of the wire is BD. BD is 100 minus L centimeter long. So what will be the resistance along this length of the wire? What will be the resistance along this length of the wire? The resistance along the length BD of the wire will be what? The resistance along the length BD of the wire. Can anyone comment here? What will be the resistance along the length BD of the wire? Yes. 100 minus L times smaller, not capital R. Okay, Himanshu commented, the Shu brothers, Himanshu, Priyamshu. But the thing is that it's not capital R. Small r is the resistance per unit length. So along this much length, the resistance will be this length into your small r. Is it okay? Yes. Now see class, things are going to be, things are at the climax here. Is it okay? Now see, at this particular point B, your bridge is balanced, right? Your bridge is balanced. And from the principle of Wheatstone bridge, if the bridge is balanced, then no current will flow through the mid resistor. That means, see, at this particular point D, there will be at this particular point D, your particular bridge is balanced. That means no current will flow through CD. No current will flow through CD. Are you getting me? So since your bridge is balanced, and from the principle of Wheatstone bridge, if the bridge is balanced, no current flows through the mid wire, through the mid resistor. So at this particular point D, your meter bridge is balanced, so no current will flow through CD. That means the ratio of the arm resistors will be equal. The ratio of your arm resistors will be equal. That means, what are your arm resistors? X upon ratio of the arm resistors will be equal. If no current flows through this mid resistor, if no current flows through this CD, then the ratio of your arm resistors will be equal. Means this resistance upon the resistance AD will be equal to this resistance upon the resistance across BD. That is what we have studied in the previous class about the Wheatstone bridge principle. So at the bridge, your meter bridge is balanced. It's balanced. Therefore, no current flows through CD. No current flows through CD. That means the ratio of the arm resistors will be equal. That means ratio of the arm resistors means X upon resistance across AD. Resistance across AD will be equal to R upon resistance across BD. Are you getting that? That is the principle of Wheatstone bridge. Is it all right? Yes. Now, this X is your unknown resistance, right? X is your unknown resistance, which I have told you at the starting point of this class. So X upon RAD, resistance across AD is small r times L. Small r times L. This R is your known resistance. I have told you at the very beginning, R is your known resistance. See? So this R is your known resistance. This value is known. And RBD means resistance across the length BD of the wire will be 100 minus L times smaller. So this smaller can be cancelled out, right? Smaller can be cancelled out. So what do we have? X upon L is equal to R upon 100 minus L. So in that case, your X will be R upon 100 minus L times L. Or we can rewrite this as R into 100 minus L upon L. So R is a known resistance. You know the value. It can be 1 ohm, it can be 2 ohm, it can be 3 ohm, it can be 0.1 ohm. L means the balanced length of the wire. L means this balanced length of the wire. It can be 40 centimeter, it can be 30 centimeter, it can be 60 centimeters. So knowing R, knowing L, your unknown resistance X can be determined. So that is how to determine the resistance of a wire using meter bridge. So the same thing, this we are studying meter bridge theoretically. Once your practical starts, you are going to do this experimentally. Any unknown resistance will be connected here, and using this formula, you can find out what is the value of that unknown resistance. Here I have connected only one unknown resistance, right? But things can be very complicated. Instead of this single unknown resistance X, you can connect two unknown resistances in series over here. You can connect two unknown resistances in series over here, like this, X1, X2. All right? Or you can connect any two unknown resistance in parallel across here. This is X1 and this one will be your X2. So in any of the ways, using this procedure, using this relation, using the principle of Wheatstone bridge, is it okay? Your unknown resistances, the combination of unknown resistance can be in series or it can be in parallel. Still then, you'll be able to find out using this application of Wheatstone bridge, which is meter bridge, and this is the required relation. Is it all right? Okay. So you can just copy it down, and once you are done with it, we'll do some of the numerical problems basing on this meter bridge. Are you done? Are you done copying? If you are done copying it down, then we can start. Okay. Priyanshu, Himanshu, they are commenting together. Okay, the Shu brothers. Okay, all right. Then, if you are done, then what I can do is I can just remove this. So in examination, questions can be asked from this meter bridge. They can be asked. Derive an expression to determine the unknown resistance using a meter bridge. That way the question can be asked. Okay. So this is the relation that you have to prove. All right. Yes. So we'll start with the numerical problems. I'll write a question. This is a resistance of 3 ohm. This is a resistance. This is an unknown resistance. Unknown resistance. Now you have a wire. You have a wire of 100 centimeter long. This wire is 100 centimeter long. The two ends of the wire are connected to a cell. The two ends of the wire are connected to a cell. Is it okay? Now this is your mid resistor, or I can just write from this point C, you have connected a galvanometer. From the galvanometer, you have connected a jockey. You have connected a jockey. Let's say that D is the null point. Let's say that D is the balance point. So this is your A, this is your B. AB is 100 centimeter long. Now, while doing the experiment, we have seen that D is the balance point, and the balance point, and if the null point is at 40 centimeter from A. If the null point is at 40 centimeter from A, so you have started from A, so the point A is at 0 centimeter, and then the point B will be at 100 centimeter. So question, if the null point is at 40 centimeter from A, find the unknown resistance X. Unknown resistance X. Class, let me work out this question for you, and from the next problem you can start doing on your own. Is it okay? Yes. Now see, already the question says the null point is at 40 centimeter from A. So the length of the wire AD will be 40 centimeter. The length AD of the wire will be 40 centimeter. So the remaining length BD of the wire will be 60 centimeter. So D is the null point. D is the balance point. So as the bridge is balanced at D, no current will flow through this section CD of the wire. Now, no current flows through the mid resistor. No current flows through this mid section CD. Then we can apply the principle of Wheatstone bridge. Means the ratio of the arm resistors will be equal. So this 3 ohm upon 40 centimeter will be equal to X upon 60 centimeter. Correct? So centimeter cancels out, 0 cancels out. So what do we have? 4 times X is equal to 6 times is 18 ohm. So your X equals to 18 by 4 ohm, which is 4 times is 16, 5 times is 20 ohm. So the value of this unknown resistance is 4.5 ohm. Are you clear with that? Are you clear with that? Yes. As the bridge is balanced at D, so no current will flow through this section. So in that case, according to the principle of Wheatstone bridge, ratio of the arm resistors will be equal. Means this resistance upon the resistance across AD will be equal to this resistance upon the resistance across this BD. Are you following that? Are you following that? Yes. So you can copy it down and I'll give you some more numerical problems basing on this meter bridge. Okay. If you're done, you please comment on the chat so as we can start on with the next problem. All right then, here goes your next problem. Is it okay? Here goes the next problem. This is your point A, this is your point B. The length of this wire is 100 centimeter long. The points A and B are connected to your battery. And then we have one more resistance here like this. So this is your 6 ohm resistor, this is your 2 ohm resistor, this is your 3 ohm resistor. This is your 4 ohm resistor, this is your X. And then from this point we connect a galvanometer, from galvanometer to the jockey. Suppose say the balance point is at D, okay? So question, if the null point is at 25 centimeter from A, then find X. Find X. If the null point is at 25 centimeter from A, then all you need to do is you need to find X. So you can start working this out. Plus, already the null point is at D. Already we have found out the null point, which is 25 centimeter from A. So the length of this wire is 25 centimeter. So the remaining length will be 75 centimeter. So we found out the null point at D, which is 25 centimeter from A. So as the bridge is balanced at this particular point, no current will flow through this section BD. No current will flow through the mid resistor, through CD. That means, according to the Wheatstone bridge principle, the ratio of the arm resistors will be equal. That means this combination upon this one will be equal to this combination upon this one. So first of all, you have to find out what is this combination. You also need to find out what is this combination. Okay? So that this upon this will be equal to this upon this. And from there you can find out what is X. Alright? I'll give you 2 minutes to solve this question. And once you give me some results, I will verify the results. Okay? Plus, you see, these three resistances are connected in parallel. So first of all, you find out what is the parallel combination. What is the parallel combination of these three, okay? The parallel combination of these three will be 1 by R is equal to 1 by 6 plus 1 by 2 plus 1 by 3. So LCM is 6, 1 plus 3 plus 2. So 6 upon 6, so 1 ohm. Or this combination is only 1 ohm. So you can redraw the figure. You can redraw the figure and write this as simply 1 ohm resistor. Is it okay? You can just simply write this as 1 ohm resistor. Now also, across this arm, since these two resistances are connected in parallel, so 1 by R is equal to 1 by 4 plus 1 by X. So LCM is 4X, X plus 4. So your R will be 4X upon X plus 4. So you can remove this and write the overall combination. You remove this and write the overall combination as 4X upon X plus 4. 4X upon X plus 4. Now, since the bridge is balanced at D, so according to the Wheatstone bridge principle, ratio of the arm resistances will be equal. That means 1 ohm upon 25 centimeter is equal to 4x by x plus 4 upon 75 centimeter. Centimeter cancels out. 25, 5 times 25, 3 times is 75. So 1 ohm is equal to 4x upon 3 times x plus 4. So 1 ohm is equal to 4x upon 3x plus 12. So if you cross multiply, 4x is equal to 3x plus 12. 4x minus 3x is equal to 12. So 1x is equal to 12. So the unknown resistance, the value of your unknown resistance will be equal to 12 ohm. Okay, the value of your unknown resistance will be equal to 12 ohm. If you are done with this, I'll give you another question. Is it okay? But that question is going to be an assignment for you. Okay, an assignment. Question: null point is observed at 40 centimeter from A. If a 2 ohm resistor is added in parallel. If a 2 ohm resistor is added in parallel to S, the null point shifts to 25 centimeter. Okay, shifts to 25 centimeter. Find R and C. So this is a question, maybe the last question for this meter bridge. And so you are going to work out with this question as a classwork, as an assignment. It's okay, home-based assessment. And then you can, after doing this classwork, after doing this assignment, you can submit it on the Classroom app, okay, on this TeachMint app. I will create a folder, so I'll create an attachment so you can start submitting this assignment tomorrow by 9 a.m. latest by tomorrow at 9 a.m. Okay. So with this topic, let me